Hello and welcome to chapter 5. I'm dealing with linear equations, and what we're doing now, we're dealing with some application, and there's only one section in chapter 5, and then there's section 5.1 where what we're dealing with is motion, especially that with a spring being weighted down by mass. And so the main part of this section is where we're going to be dealing with second order differential equations with all coefficients being constants. So basically piggybacking on chapter 4, so this is why this comes next. And so what we're going to try to do is we're going to try the find the original function, the position function of our weight, whatever we're using for our springs, given starting off with our differential equations. And so starting off with our first part is going to be free and undamped motion, which is is not really going to be useful, but it is a good starting point, because whenever we are weighted down by a spring, whenever we pull this spring down, it's not going to continue in that motion forever. And this is what free and damped motion is that after you initially release your weight, it's not going to keep the same type of motion. So pretty much what the graph of that would be as soon as we release it, the spring is always going to have the same distance from the equilibrium position. It's going to continue to go the same amount of amplitude. And for any spring, we know that it's going to go back to rest in the equilibrium position, which mainly the graph would look like this. And we're going to talk about this in our next example, where initially it does have a high amplitude, but then it gets smaller to go back to the equilibrium position. And I can represent this by some dotted lines just to show that it's going back to the equilibrium position, but free and damped motion is basically representing this model. And so we're going to start off using Hooke's law. Suppose that a flexible spring is suspended vertically from a rigid support and a mass m is attached to its free end. By Hooke's law, the spring exerts a restoring force opposite to the direction of elongation and proportional to the amount of elongation s. So our force, whatever we're using to bring down our spring, is going to be represented by k times s, some constant times s. So here's the spring unstretched. When we apply the force to it, when we apply the weight to it, it brings it down by a distance of s, and we're going to be able to find our force by multiplying some constant times that distance. That distance s is how far it takes for our weight to bring the spring down to get to an equilibrium position. Now we're going to use Newton's second law to help us with finding our initial function, which is going to be our position function. And so Newton's second law is after a mass m is attached to a spring, it stretches the spring by amount of s and attains a position of equilibrium at which its weight w is balanced by the restoring force ks. So one thing to recall is that our weight is not necessarily our mass. Our weight is just equal to the mass times g, times that pull of gravity. Now, usually we measure mass in either slugs, kilograms, or grams. Now, because it's giving to us in pounds, the way that we can convert this is using the 32 feet per second squared if we're given our distance in feet. Now again, if we're still using pounds but we're given our distance in meters, then we can use the 9.8 and for our pull of gravity. And if we're using centimeters, our pull of gravity would be 980 centimeters per second squared. We're mainly going to be dealing in pounds, and so we're going to be using this first pull of gravity, g, 32 feet per second squared. So if the mass is displaced by an amount x from its equilibrium position, the restoring force of the spring is then k times x plus x, whatever the x represents the amount that we're displacing from the equilibrium position. Assuming that there are no retarding forces acting on the system, and assuming that the mass vibrates free of other external forces, so free motion, we can write, basically this is force equals mass times acceleration, where this is our mass. Acceleration is the second derivative, and that's equal to our force, which we have here, which is negative kx plus s plus mg. Now, from this, we know that our negative ks plus mg gives us back to our equilibrium position, so that technically just equals 0. So our force is going to be given by negative kx, where x is the amount that is being pulled. And so here we have our second order differential equation, and what we want to do is we're going to bring everything to one side, and we can write our second order differential equation as m times the second derivative plus kx equals 0. Now, important to note that anytime that we are above the equilibrium position, we're going to be negative, and anytime we're below the equilibrium position, we're going to be positive. That also starts with if our velocity is going upward, that's also negative, and if our velocity is going downward, then that's positive. So now, here we have our second order differential equation, and what we want to do is we want to write this in terms of something that we can solve. So we want to get rid of our leading coefficient, our leading constant. So we divide everything by m, and we're going to get this form, the second derivative plus k over mx equals 0. And what we're going to do is we're going to rewrite k over m to be another variable, and we're going to say that k over m is equal to omega squared. It looks like a W, but that's omega, so omega squared. And therefore, we can write our second order differential equation as the second derivative plus omega squared x equals 0. And this is the form that we want to have a lot of our equations in, just to get to what our position function would be. So once we get everything into, once we are able to find all of our values, we can see that, okay, this is the type of differential equation that we're dealing with. It's free undamped motion because we don't have that first order, we don't have that derivative that should be in here in the middle. So then we can solve for x of t. And when we solve this for x of t, we're going to need to find our c sub 1 and our c sub 2's. The way to find the c sub 1 and c sub 2 is going to be given by the initial position and then the initial velocity. So to find the solution, how to actually get to the position function, we're going to rewrite this and say the second derivative is just m squared plus w squared. Set that equal to 0. Solve for m. When we do, we're going to get m is equal to plus or minus the square root of negative omega squared, which is just equal to plus or minus omega times I. So we have a complex number. Because we have complex number, or a complex solution, we're going to plug this into cosine and sine. And so our alpha is 0, our beta is the omega, so therefore our position function is x of t is equal to c sub 1 cosine of omega x plus c sub 2 sine of omega x.